The next exercise is to write a consultancy report. This is different to a scientific paper. The differences really come at the start, in that there's not a requirement for you to justify the work in the same way as you would with a scientific paper. The reason for this is because you've been given the task to do, supposedly by a client. This is a sort of report that you'd write if you were working in the environmental sector as a consultant. So you've been given a task, so you don't need to justify why you're carrying the task out. Beyond that difference, though, you should try and make the report as much like a scientific paper as possible. Generally in consultancy, the pressures of time are such that it's hard to do that, but the ideal would be for you to write it as carefully and coherently as a scientific paper. Typically when you look at consultancy reports, you'll find that isn't the case, and it's shown by the fact that they have an awful lot of subheadings, and often numbered subheadings. So the structure of the report isn't actually built into the writing necessarily. There's a structure there because you've got one paragraph numbered 1 and another paragraph numbered 2 and then 3 and then 4. So that means that they don't actually spend the time sorting the structure out from one point to follow another, because they can just write point number 1, point number 2, point number 3. So, however, the more you can make your writing of sufficient quality that the argument flows from one point to the other, then the less you should need to write those subheadings. The subheadings are also useful for finding your way around a document that needs to be referred to. So that's another reason why it's done in a consultancy report and not so much in a scientific paper. Anyway, the exercise is, in this case, the assessment of atmospheric emissions by Gaussian plume modelling. This type of atmospheric emissions modelling is typically the sort that's carried out in most consultancies. It relies on the little bit of mathematics that you've been covering so far, which is looking at the normal distribution. We'll go into that a bit further. There are more sophisticated models that are built around the same mathematics. This is a very simple version, and there are now more complicated models that are used at more specialist consultancies. For you, the client is a developer. They're building a new power station, and it falls under the Large Combustion Plant Directive that requires an environmental statement, and you're tasked with producing the environmental statement and one particular part of it, which is concerned with the atmospheric emissions from the power station. The power station serves the needs of Richtown, and we're concerned about the exposure of populations that live in the area. It's in a valley in Filshire, and the wind is very constant and be regarded as unidirectional. You can return to some of these points when you get further into your report. The prevailing wind blows from the power station site towards the two towns of Filth and Richtown. You've got the locations of the towns, and you've got some meteorological information given to you, and then some detail of the annual release, and the height of the stack. That's the chimney. The stack is the chimney. They've got options of either building a 20 metre high or a 60 metre higher stack. And there's a requirement to find out what the exposures are in the towns of Filth and Richtown, depending on whether you've got a 20 metre or a 60 metre stack. The starting point for this has been given to you. Let's say here. There's the title. There's not much in the way of justification because you've been asked to do this. But then this report presents the output of a predictive model of the resultant ground level contaminant concentrations resulting from the proposed releases. In order that the reliability of the predictions can be assessed, the work is prefaced by justification for the Gaussian dispersion model used. So first section is to justify the methodology. Now this is really for your client, demonstrate that the methodology that you're going to use is appropriate, and also what will come out of that after you've been through the methodology is that you can then criticise the results that are produced by it, because you've made the assumptions of that methodology explicit, and that will be the second part of your report. So first of all, we need to go through and justify the methodology, then we'll produce the results from it, and then we can criticise, well, first of all discuss the implications of those results and criticise those results. Again, it's the standard sort of procedure that you'd have in your scientific papers as well. We'll get the result and then criticise the result. But first of all, we need to justify the methodology. In order to do that, it's best to look at the document, the atmospheric guidance note, and the justification for the methodology begins really first by considering the scale at which we're trying to predict the distribution of the contaminant. The scale is such that we're working at a scale of a few kilometres. If we were working at scales of hundreds of kilometres from an emission, then those emissions would have to be emissions that had made it all the way through to the upper atmosphere. So when you have a very large volcanic explosion, for instance, that allows material to be carried through to the stratosphere, then you get very widespread dispersion, and the modelling of that sort of dispersion is different to the modelling of dispersion in the lower atmosphere. Our emissions are in the lower atmosphere and they don't make it into the upper atmosphere. In the upper atmosphere, dispersion is controlled by fairly predictable winds. The geostrophic wind, which blows from high pressure to low pressure but deflected to flow parallel to isobars because of the Coriolis effect, and the jet stream, these winds are fairly predictable, and a lot of effort goes into predicting the behaviour of those winds. But they're not appropriate for the dispersion in the lower atmosphere that you're going to be looking at. In the lower atmosphere, the air movements are turbulent. So we've got a turbulent mixing zone in the lower atmosphere, and the turbulence results from the roughness of the ground. So buildings, plants, vegetation cause the ground to be rough, and consequently the air turns over in a turbulent manner. Where you've got turbulent air movements, then dispersion, the movement of the particles, is effectively random. Now, that just strike a chord with you, because we've considered what controls the distribution of whatever it might be, student heights or particles. We've looked at diffusion, we've looked at particles. If the processes operating to cause them to disperse are effectively random, and recognise that the distribution that we're likely to get is a normal or Gaussian distribution. If we take the frequency of particles to be the concentration, which is what they are, then we can have a frequency distribution, and the frequency distribution for the particles, which is a concentration distribution, we'd expect that to be a normal distribution. If a section were taken across a plume of polluted atmosphere, the frequency of occurrence, or the concentration of the particles, would be low at the edges, as it would be unlikely that a particle could travel very far in one direction toward one edge. But the frequency of occurrence or the concentration would be highest nearest the source, as on average the random movements result in no net movement. So far you've considered a normal distribution as being a bell-shaped curve. If we're going to apply that in the environment, then actually it needs to be in 3 dimensions. So if you imagine spinning your bell-shaped curve through 360 degrees, then you actually have a bell shape, and that would be the distribution of contaminant that you might expect if there's nothing to disturb that distribution. So there's no wind blowing, but if you've got a contaminant released, then the distribution around it, the mean concentration would be the highest concentration would be in the middle where the release had occurred, and then around that the concentration would drop off as you move further away from the emission source. In the case of Filshire, this power station, there's a constant wind blowing down the valley, and that's going to extend that distribution in the downwind direction. So if there were no prevailing wind, dispersion would be equal in all directions, but with the prevailing wind blowing in one direction, then dispersion along the x-axis, if you like, would be actually wholly a function of the wind speed. So predicting in the direction of the wind just requires knowledge of the wind speed. We assume that the rates of dispersion are in the vertical directions, and in the crosswind directions are much less than the dispersion brought about by the wind blowing in the downwind direction. If you look on your notes, there's a little diagram showing this. Here's a plume. In this case it's come up from a stack, and there's actually some stat rise which we're not going to take into account, which is an extra bit of rise because the gases are hot. But once they've cooled down sufficiently and they're moving in the downwind direction, you can see across wind we've got a normal distribution, and then vertically as well we've got a normal distribution. Whereas in the downwind direction the concentration really is just predicted from the wind speed. So we're not seeing a normal distribution in the downwind direction. That sort of random dispersion is overwhelmed by the movement of the wind, the downwind direction. So we've got normally distributed concentration across the wind and also vertically. So we've got a model that we can justify. The part of the atmosphere we're working in is the turbulent zone in the lower atmosphere. Turbulent motions of the atmosphere are effectively random motions, and therefore particles that are moved with these random motions will be normally distributed. The normal distribution is then projected into 3 dimensions. In order to use the model, we need to define particular normal distributions. We've seen that a normal distribution is a family of curves with an infinite number of members, and in order to define a particular normal distribution we need a mean and we need a standard deviation. The standard deviation is the index of the amount of dispersion. In this case we call it a dispersion coefficient. The magnitude of these dispersion coefficients, which we need to put into our model, are going to be determined by the prevalent atmospheric conditions that control mixing. And the most important of these atmospheric conditions that control mixing, and which will relate to dispersion coefficient, is atmospheric stability. Now we must have a short discussion about atmospheric stability. The most important control on mixing is atmospheric stability, and then there's 4 little graphs which explain lapse rates. And to think about these we use a concept that meteorologists use, and you'll be hearing more about this, well I think you will have heard already in your second year course, and you'll hear more in your meteorology course in third year, but considering parcels of air. What the little graphs are showing are height in the atmosphere against temperature, and there's 2 lines plotted on there. We're actually most interested really in this green one, which is the unsaturated lapse rate, known as the dry adiabatic lapse rate, the DALR, dry adiabatic lapse rate, and that's showing the rate of temperature decrease with altitude. The reason why temperature decreases with altitude is because pressure decreases with altitude. As the pressure decreases, the temperature will decrease. Given that the depth of the atmosphere is effectively constant globally, then you might expect the dry adiabatic lapse rate to consistently define the atmospheric temperature profile. So you'd expect this to be globally relevant, this lapse rate. This would also be the lapse rate that you'd expect for the parcel of air that we said we were going to consider. So a parcel of air moving in the atmosphere, you'd expect its temperature to change as it rose through the atmosphere in the same way as this dry adiabatic lapse rate. It would change because of the decrease in pressure. So the dry adiabatic lapse rate is the lapse rate that you'd expect to operate on a parcel of air moving in the atmosphere. However, the temperature profile in the atmosphere is not controlled only by pressure changes. There's also variations in heat input to the system. Heating by the sun effectively reverses the relationship of temperature and altitude, i.e. increasing temperature with altitude in the very upper atmosphere. In the troposphere, the bottom layer that we're interested in, temperature changes are well described by the dry adiabatic lapse rate, but you can get differential heating resulting in the existence of temperature profiles that are not the product of the dry adiabatic lapse rate. So we can locally get lapse rates that are not this theoretical global dry adiabatic lapse rate. You can think about why that might happen. We think about the sun heating from the top, depending when that's happening, how warm the ground is as well. You can get the ground being warmer than the air above it, which is something that you'll have come across, and you'll know what the name for that is as well. And we can mention that as we go on. Having established then that we have this dry adiabatic lapse rate, which is globally prevalent, however it may be locally different. If you consider the behaviour of a parcel of air, the parcel of air will change temperature as a result of the change in pressure on it, and therefore it will tend to follow the dry adiabatic lapse rate unless there's some special condition. That red line is a special condition in some ways because that's a parcel of wet air. But let's just consider the green line, which is the parcel of dry air. That parcel of dry air would change temperature along the dry adiabatic lapse rate. If the local lapse rate was also the dry adiabatic lapse rate, then at any point that parcel of air is going to be surrounded by air that's also at the same temperature. As it's at the same temperature, it's going to have the same density. However, if the parcel of air rises and changes temperature according to the dry adiabatic lapse rate, the green line, but the local lapse rate is one in which the temperature changes more rapidly with altitude, which we've got illustrated down here, where it states unstable, then as the parcel of air rises and cools at the dry adiabatic lapse rate, it's actually going to be warmer than the air around it, because the air around it is cooling faster. So as the parcel of air rises and only cools at the dry adiabatic lapse rate, then the surrounding air will actually be cooler than the parcel of air. If the parcel of air is warmer than the surrounding air, then it will be less dense and therefore it will be more buoyant, and consequently its rise will be accelerated. And that's why this state of the atmosphere is called unstable, because air will tend to rise. It's an unstable atmosphere. Air that's lower down starts to rise, will rise more and more rapidly. It's an unstable condition. The atmosphere wants to turn over to try and remedy this lapse rate, this local lapse rate, which is cooling more quickly with altitude than the dry adiabatic lapse rate. That's the unstable condition. And the opposite of that, the very opposite of that, is this condition, which is called an inversion. The inversion has the temperature, the local temperature, actually increasing with altitude. The local temperature increasing with altitude. Now that can happen when the ground is very, very cold. So if the ground's very cold, as you move away from the ground, then the air can actually be warmer than the ground. And that can happen in the morning, on a very cold morning, when the ground's been cooling all night, and then the sun starts to shine, and it manages to warm the air up above the ground before it can warm the ground up. And it's called an inversion, which is a term you've heard before. The reason it's called an inversion because it's inverting the normal lapse rate. You've got a lapse rate of increasing temperature with altitude instead of decreasing. If you consider the parcel of air then that's cooling due to pressure change as it rises, the parcel of air is actually going to always be much colder than the air around it if you've got a local temperature inversion. And if the parcel of air is colder than the air around it, it's going to be more dense than the air around it and not buoyant. Consequently, it won't rise, and therefore there'll be no vertical mixing at all. Less extreme version, you've got the local lapse rate, which is showing we've got the same temperature with altitude. The temperature is not decreasing with altitude, but as long as the temperature decrease with altitude is less than the dry adiabatic lapse rate, then you're going to have stable conditions in which there'll be no vertical mixing. Neutral conditions drawn here is when the dry adiabatic lapse rate and the local lapse rate actually coincide. In the little diagram here, that's the local lapse rates drawn through between the saturated and unsaturated. But really, as far as this exercise is concerned, just consider the unsaturated, the dry adiabatic lapse rate. So there's an explanation then of atmospheric stability. And atmospheric stability is the major control on mixing in the atmosphere. It controls mixing in the atmosphere because atmospheric stability is defined by the relationship between the local lapse rate and the dry adiabatic lapse rate, which is the lapse rate that's felt by a parcel of air as it tries to rise and cools due to decrease in pressure. So under unstable conditions we would expect to have much larger dispersion coefficients, much larger standard deviations for the concentration distributions, whereas under stable conditions, as we get under an inversion, we would expect the dispersion coefficients to be low because there'd be little or no vertical mixing. These conditions then, ranging from an inversion through stable to neutral to unstable conditions, have been studied for a long time, and they've been categorized into 6 different categories of stability, and these are known as Pascal stability categories. These Pascal stability categories, as well as splitting the stability into 6 different classes, there's a range of other meteorological variables that have been observed to be associated with each of those stability classes. The ones that are particularly relevant to you are the wind speed. So there's particular wind speeds that are often associated with each stability category. There's also the amount of sunlight as well. So that's sufficient information for you to justify your argument.